In this problem, we have an insulated beaker with negligible mass, contains 0.25 kilograms of water at a temperature of 75 degrees Celsius. How many kilograms of ice at a temperature of negative 20 degrees Celsius must be dropped into the water to make the final temperature of the system 30 degrees Celsius? All right, so insulated beaker means the sum of all the Q's, the energy exchange because of different temperatures, those need to add up to be 0. Since they told us the beaker's negligible mass, we really only have the water and the ice to worry about. So Q of the water plus Q of the ice is going to equal 0. The water will cool down, so it's going to have a negative Q. The ice, well, it has to get to its melting temperature and then melt and then also increase in temperature. So we have to account for each portion of energy it needs, but it's eventually going to warm up to this final temperature. All right, so from the test notes, we know C of water is 4190 joules per kilogram Kelvin. C of ice is 2090 joules per kilogram Kelvin. We will need the latent heat of fusion because we need to take the ice from the solid phase into the liquid phase. So that one is 3.33 times 10 to the 5th joules per kilogram. All right. So the water is only going through a temperature change. So Q of the water is just going to be mass of the water, C of the water, delta T of the water. The water itself is just starting at a temperature of 75 degrees Celsius and ending at a final temperature of 30 degrees Celsius. So it's only going through a temperature change. The ice, we're trying to find the mass. But because the ice is initially at negative 20 degrees Celsius, well, that's not its melting temperature. So if we start putting energy into the ice, it's not going to melt, it's going to increase in temperature. So we need to first account for the change of temperature from negative 20 degrees Celsius to 0. We have to get the ice to its melting temperature. Once we put in this much energy, we still have ice, but it's now at 0 degrees Celsius, which means it's now at the point it can melt. So as we continue adding energy, the M times L, we're going to melt the ice. But after this much energy, we still have 0 degrees Celsius. We happen to have liquid water though. So we need to continue adding energy. Now that this is water, so liquid, we have to continue adding energy until we get to the final temperature. I don't know what to call this. Ice that is water now? Ice/W? I don't have a good name for that one. So this is to bring the water that was ice to the final temperature of 30 degrees Celsius. So all of this needs to add up to be 0, because the energy is going to be exchanging within this insulated beaker. All right, so our water, we have 0.25 kilograms of water. C of water is 4190. The final temperature of everything is 30 degrees Celsius. The water, though, was initially at 75 degrees Celsius. So we know how much energy that the water ends up giving off, or at least we can calculate that. Notice we'll have a negative number here because T final is smaller than T initial. But hopefully that makes sense. The water is cooling off, so it's giving away its energy. We don't know the mass of the ice. That's what we're looking for. In this first step, it is still ice, so we have to use C of the ice. It is ending up at 0 degrees Celsius, starting at negative 20 degrees Celsius. So we're taking the ice from its initial temperature of negative 20 up to its melting temperature so that we can melt it. The melting temperature, once we're there, then as we continue adding energy, we'll now melt it. That's the mass times L sub F. And then once it's melted, as we keep adding energy, it's liquid water now, so we need to use C of water. And it's going to end up at this final temperature of 30, having started at 0 in the liquid state. So we have essentially these three terms all have mass of the ice in it. So if I go ahead and factor out mass of the ice and multiply all those numbers together, and here I'm getting 500, 500. It's an interesting number. The water term, I'm getting negative 47137.5. But negative, again, that means energy's leaving the water that was originally water and going into this ice. Sorry, there's a lag again with my computer, so it's taking a second to display what I'm writing. I'm getting 0.0942. This will be in kilograms, because we have our kilograms, our mass of water in kilograms, all the constants are in terms of kilograms. If we want, we could say 94.2 grams. Either way is fine. Now, just a reminder, I mentioned this in a previous video. It's very common to want to say Q of the water is going to be Q of the ice, which in general is true, but that's true in terms of the absolute values. The amount of energy the water gives to the ice does equal the energy the ice takes in. But mathematically, if you want to start just an equality, you have to say that Q of the ice is the opposite of Q of the water, because Q of the water ends up being negative when we put in delta T. So just be careful with the signs. Missing that minus sign, of course, will give you an incorrect answer.